Now that we've seen how to pick an op-amp, let's look at how to actually use an op-amp in a circuit. What we've seen till now is that the op-amp gives us an equation like Vout is equal to the gain times V plus minus V minus. So one could say that I will give the negative input to ground and the positive to Vin. So using this, I should basically get a Vout, which is Vin times the A of the circuit, because V minus is 0. But what happens in real life is that this A is very inaccurate. Say if you want an A of 10 raised to 4, it can go from anywhere from 10 raised to 3 to 10 raised to 5. And that creates a very big problem, especially since this is such a large number. So if say Vn is 2, so instead of 2 into 10 raised to 4, the Vout can go from like 2 into 10 raised to 3 to 2 into 10 raised to 5. Also, these are very high voltages and we almost never want to work with such high voltages. So, and even if you try to reduce A, like say if you want an A of 2, getting it of exact 2 is next to impossible. It can go anywhere from 0.5 to like 5. So engineers tried very hard to look for a solution to this problem, and they found a solution which now when we look at it, it probably will seem to you that if you were born before them, you could have come up with it yourself too. It's a very interesting solution. Let's take an example of driving on a road. This is the car that you're driving. Ideally, you would want your car to move in a straight line. But let's say your steering wheel is very inaccurate. It has only two possibilities. It can either go right or go left. Let's say in the beginning, you go right, and this is how your car ends up. You realize that this is where you were supposed to be, and this is where you are. So there is an error in the right direction. So you will basically create an error correction in the opposite direction. And then once you move to the left, your car might go this way. Again, you realize that there's an error from here to here. This time, most probably the error is going to be smaller than the previous time. And you create an error correction again in the opposite direction. So this was the error direction and you moved in the opposite direction, so that eventually you come back onto your straight path. So that there can be a lot of disturbances in the driving which can cause your car to keep going right or left, but you have a mechanism where you move in the direction opposite to the error and thus come back to the correct path. That's exactly what we do in an op-amp, and we call that negative feedback. It's called negative because we move in the direction opposite to the error. So let's see how this actually happens in a circuit. So we have an op-amp. This is the Vout. So what we are trying to do is, if our Vout is supposed to be some ideal value, because of some disturbance the Vout increases. We want some kind of mechanism which will pull the Vout back down. So from this formula we can see that the easiest way to pull Vout down will be to increase V minus. Now we need to find an increasing signal, but our Vout is anyway increasing. We have an increasing signal right here. So what we do is we feed the Vout into the negative input. So let's analyze what exactly is happening here. If Vout increases from what it's supposed to be, V minus also increases. As a result, the difference Vn minus this becomes smaller. As this becomes smaller, the smaller number into A becomes smaller, and thus Vout comes down. Opposite case, say in the beginning, say Vout decreased from the value it's supposed to be at. Again, the V minus is going to decrease. So the difference between Vn and V minus is going to increase, and that will cause Vo to go back up. So basically, if any kind of problem happens at Vo, The same thing appears at V minus, and since V minus has a negative relation with VO, it causes the VO to move in the opposite direction, and thus the error gets corrected. Now, the main benefit of this is that the error correction simply does not depend on the value of A. A can be we don't, as long as A is a large number, we don't really care what A is. Okay, why do we want A to be a large number? That is because we had said that VO has to be a constant, and if A is infinity, we know that this term is 0. So we can make the two terminals equal, and that helps us for analysis as well as for design, and we want that to be true. That's why we make A as large as possible. But besides that criteria of being as large as possible, we don't really care whether it's 10 raised to 4 or 10 raised to 5 or 10 raised to 6 or any other large number. And that makes the designs of operational amplifiers a lot easier, and that's basically the revolutionary idea which made operational amplifiers so popular. So this circuit that we have here, where we basically connected the output to the negative input, and we gave an input voltage at the positive terminal. Let's see. So let's try to find out what exactly is this value going to be. We know that since we've assumed A to be infinity and V out to be a constant, the two terminal voltages have to be equal. We know that the positive terminal voltage is input, so the negative terminal voltage is also input, and negative terminal is shorted to V out, so V out is also equal to V in. And this circuit is called a buffer. Negative feedback is used to make very interesting circuits with the operational amplifier, some of which we'll see in the next lectures.